Good evening, students. Good evening, students. In this live session, I am going to discuss in detail about the water technology and multiple choice questions based upon water technology. Especially in this chapter, we are going to discuss about the types of water, types of hardness, disadvantages of hard water, what is meant by total hardness, units to express total hardness, removal of hardness, that means softening methods, municipal water treatment, and finally we are going to discuss about desalination of seawater. So, water can be classified into two types, namely soft water and hard water. So, depending upon the action of water with soap solution, water can be classified into two types, soft water and hard water. So, the water which produces lather easily with soap solution is called as soft water. So, water which produces a lather easily with soap solution is called soft water. On the other hand, water which does not produce lather easily with soap solution is called as hard water. So, here what is our point of interest? Why soft water produces lather immediately with soap solution, whereas hard water does not produce lather easily with soap solution. Here soap means it can be considered as sodium or potassium salt of stearic acid, that is C17H35COONA. So here C17H35COONA is called as sodium stearate. So it is the formula of soap. So whenever soap is mixed with water, initially it produces stearic acid. So initially it produces stearic acid. So this stearic acid C17 H35 COOH reacts with soap and that results in the formation of leather. So if the water is soft, it produces leather more readily. So coming to the hard water, let us see what happens when hard water is mixed with soap solution. So whenever hard water is mixed with soap solution, that hard water consists of dissolved salts of calcium or magnesium. So in that hard water, dissolved calcium or magnesium salts will be present. So whenever the soap is mixed with hard water, it is the hard water. Hard water contains dissolved calcium or magnesium salts. These dissolved calcium and magnesium salts are responsible for the hardness. So, whenever soap is mixed with hard water, initially it reacts with dissolved calcium and magnesium salts. Then, it results in the formation of calcium or magnesium stearates. It results in the formation of calcium or magnesium stearates, which is a white dirty precipitate. So actually it is the white dirty precipitate. This reaction proceeds until all the calcium and magnesium salts present in the hard water consumes. Then it reacts with water and produces leather after some time. So hard water does not produce leather immediately with soap solution. This is due to the presence of dissolved calcium and magnesium salts. So let us see what is the reason behind the hardness. So especially hardness of water is mainly due to the presence of dissolved calcium and magnesium salts. So especially hardness is due to the presence of 6 important dissolved salts in water, namely calcium bicarbonate, magnesium bicarbonate, calcium chloride, magnesium chloride, calcium sulfate and magnesium sulfate. So 6 salts are responsible for the total hardness, namely calcium bicarbonate, magnesium bicarbonate, calcium chloride, magnesium chloride, calcium sulfate and magnesium sulfate. Again hardness can be classified into 2 types, namely temporary hardness and permanent hardness. Temporary hardness is also known as carbonate hardness, whereas permanent hardness is known as non-carbonate hardness. Especially the hardness is expressed in terms of calcium carbonate equivalents. Since it is the most insoluble salt that easily precipitates out from the water, and the molecular weight of calcium carbonate is 100, which makes calculations more easy. So, the concentration of any salt can be expressed in terms of calcium carbonate equivalents. So, what is the formula that is used to express hardness in terms of calcium carbonate equivalents? That is equal to weight of salt divided by molecular weight of the salt into molecular weight of calcium carbonate, here that is 100. So this formula is highly useful for the conversion of the concentration of hardness producing salts in terms of calcium carbonate equivalents. So especially, what are the units that are used to express total hardness? Especially coming to the units, hardness can be expressed in terms of ppm or mg per liter or degree French or degree clock. So what are the units used to express total hardness? ppm or mg per liter or degree French or degree clock. So 1 ppm is equal to 1 mg per liter, and that is equal to 0.1 degree French, and that is equal to 0.07 degree clock. This is the relation among the units. So coming to the removal of hardness, that can be done through softening methods. Especially hardness is mainly due to temporary or permanent. So initially, how to remove temporary hardness? Let us see how to remove temporary hardness. Removal of temporary hardness, and this can be done by following any one of the methods. One is simply by boiling. So whenever water is boiled, then what happens? Especially it contains calcium bicarbonate or magnesium bicarbonate. So temporary hardness is mainly due to the presence of calcium bicarbonate or magnesium bicarbonate. So whenever water is boiled, then what happens? The calcium bicarbonate will be converted into calcium carbonate, that is a precipitate, along with the formation of carbon dioxide and water. So similarly, whenever magnesium bicarbonate is present, then that will be converted into magnesium hydroxide, along with the formation of carbon dioxide. So in that way, the calcium salts are precipitated out into calcium carbonate, whereas the magnesium salts are precipitated out into magnesium hydroxide salts. And we are having one more method, that is Clock's method. So in this method, always the calculated amounts of lime will be added, especially slaked lime will be added. Slaked lime means calcium hydroxide. Let us see then what happens. So whenever if the hard water contains calcium bicarbonate or magnesium bicarbonate, then if that water is treated with calcium hydroxide, initially all the calcium salts will be converted into calcium carbonate. So what happens? All the calcium salts will be converted into calcium hydroxide along with the formation of water. And coming to the magnesium bicarbonate, here magnesium bicarbonate reacts with slaked lime and that results in the formation of magnesium carbonate plus calcium carbonate plus water. So in that way, all the salts that are responsible for the temporary hardness can be precipitated out from the water. Clear? Let us discuss how to remove salts which are responsible for the permanent hardness. That is removal of permanent hardness. That can be done by following internal treatment of water or by following external treatment of water. So, for the removal of permanent hardness, we can either follow internal treatment of water, we can also follow external treatment of water. So, especially coming to the internal treatment of water, we are having different methods for the removal of internal treatment of water. So, coming to the internal treatment of water, here an ion, that means which ions are responsible for the permanent hardness, calcium or magnesium ions or chlorates or sulfates. So in this method, an ion is prohibited to exhibit its original character by converting it into more soluble salt or by forming a complex. So when these ions are present in water, they are responsible for the total hardness. So in order to remove permanent hardness from the water, here these ions are prohibited to exhibit their original character and thus permanent hardness can be removed from the water. And here we are having different techniques. So coming to the internal treatment of water, permanent hardness can be removed either by colloidal conditioning. In that way, we are having 5 different methods. Coming to the colloidal conditioning, here especially water is treated with kerosene or agar agar or with tannin. Then these chemicals will form a coat on hardness producing salts, and thus they will be prohibited to exhibit their original character. In that way, the permanent hardness will be removed. Coming to the phosphate conditioning. In this phosphate conditioning method, especially sodium phosphate will be added to the hard water. For example, this hard water consists of calcium chloride. Then what happens? Here anions will be exchanged. With the result, it results in the formation of calcium phosphate and sodium chloride. If calcium chloride is present in the water, it is responsible for the permanent hardness. If that calcium is present as calcium phosphate, chloride as sodium chloride, they are not responsible for the hardness. In that way, the permanent hardness will be removed from the water. Coming to the carbonate conditioning. In this method, sodium carbonate will be added. Let us suppose that calcium sulfate is responsible for the permanent hardness. Then you just exchange the anions. Then it results in the formation of calcium carbonate and sodium sulfate. So, calcium sulfate is responsible for the permanent hardness. Whenever anions are exchanged, it results in the formation of calcium carbonate. It is not responsible for the permanent hardness. And sodium sulfate is also not responsible for the permanent hardness. In that way, permanent hardness can be removed from the water. Next, coming to the Kalgan conditioning. It is very important. Here, permanent hardness can be removed by the addition of Kalgan. Kalgan means it is sodium hexametaphosphate. So, whenever Kalgan is added to water, initially it dissociates into sodium ions along with the formation of a complex ion. So, it is the complex ion. So, this in particular reacts with hardness producing salts. Let us suppose that calcium sulfate is responsible for the hardness. You just exchange the cations. Then it results in the formation of calcium complex ion along with the formation of sodium sulfate. So these are not responsible for the permanent hardness. Okay. Moving to the fifth method, that is by the treatment with sodium aluminate. So fifth method generally involves the treatment with sodium aluminate. So in this method, sodium aluminate will be added to the water. Then initially it results in the formation of sodium hydroxide along with aluminium hydroxide. Here this sodium hydroxide especially reacts with magnesium chloride that is responsible for the hardness. And here the magnesium chloride will be converted into magnesium hydroxide. It is a precipitate which can be removed from the water more readily. So in that way, the permanent hardness can be removed from the water more readily. That is all about the removal of permanent hardness through internal treatment of water. Next, we will discuss about the external treatment of water, which involves three different techniques. One being lime soda process. The first method is called as lime soda process. In this method, lime and soda calculated amounts of lime. Lime means calcium hydroxide and soda means Na2CO3 will be added to the water. Then what happens? All the calcium salts will be converted into calcium carbonates. They will be precipitated out, whereas all magnesium salts are precipitated out into magnesium hydroxide. So whenever water is treated with calculated amounts of lime and soda, all the calcium salts will be precipitated out into calcium carbonate, whereas magnesium salts will be precipitated out into magnesium hydroxide. By this method, it is possible to remove hardness up to 15 to 30 ppm. Moving to the second method, that is called as zeolite process. So coming to the zeolite process, it is sodium zeolite is hydrated sodium aluminosilicate. So what is zeolite? Zeolite is hydrated sodium aluminosilicate. It is a porous material. Here the value of X varies from 2 to 10, whereas the value of Y varies from 2 to 6. Actually here the sodium ions are highly active and simply it can be represented as sodium zeolite. How it can be represented? It can be represented as sodium zeolite. So whenever water is passed through the sodium zeolite, it is capable of exchanging its cations, especially its sodium ions, with the cations responsible for the hardness. That means calcium or magnesium ions are the cations that are responsible for the hardness. So whenever water is passed through sodium zeolite bed, then it is capable of exchanging its sodium ions with cations responsible for the hardness, that means calcium or magnesium ions. Then it results in the formation of calcium zeolite or magnesium zeolite along with the formation of sodium ions. So whenever hard water is treated with zeolite, it results in the formation of calcium zeolite or magnesium zeolite. After some time, this zeolite bed will be exhausted. That means no sodium ions will be present. Only it contains calcium zeolite or magnesium zeolite. At this moment, it should be regenerated. So coming to the regeneration of exhausted zeolite bed, that can be done by using brine solution, that is 10% NaCl solution. So whenever the exhausted zeolite bed, that means calcium zeolite or magnesium zeolite is treated with NaCl solution, then again it results in the formation of zeolite. Here the zeolite will be again regenerated. And this method is highly useful for the removal of hardness up to 10 ppm. Here the zeolite bed is porous in nature, that's why turbidity of water should be less than 10 ppm. And also especially whenever acidic water is passed through zeolite bed, acidic water will destroy the zeolite bed. So always water should be examined in order to know the nature of the water. If acidic water is used, it destroys the zeolite bed. Next, moving to the third method, that is called as ion exchange method. This is the best method for the removal of permanent hardness. Since here by this method hardness can be removed up to 2 ppm, and hence this method is highly useful for the treatment of boiler feed water. Especially ion exchange process is also known as deionization process or demineralization process, which involves the usage of two ion exchange resins, one being cation exchange resin and the other is anion exchange resin. So simply cation exchange resin can be represented as RH and anion exchange resin can be represented as ROH. So that means here it consists of acidic group, whereas anion exchange resin consists of basic group. So initially when water is passed through cation exchange resin, let us see what happens. So this is the cation exchange resin. When water is passed, it contains either calcium or magnesium cations. Then what happens? Then it results in the formation of calcium salt or magnesium salt along with the formation of H plus ions. And when water is passed through anion exchange resin, that is R dash OH plus, let us suppose that chloride ions are present, then it results in the formation of chlorides and OH minus ion. So now water contains H plus and OH minus ions. They combine and results in the formation of water which is devoid of all types of ions. That's why it is called as deionized water or demineralized water. So after some time these cation and anion exchange resins will be exhausted. Let us see how they can be regenerated. Coming to the regeneration of cation and anion resins. Initially, cation exchange resin can be regenerated by washing with dilute HCl or dilute sulfuric acid. That means, let us see, whenever the exhausted cation exchange resin is washed with dilute HCl or dilute H2SO4 solution, it readily reacts with H plus ions and results in the formation of cation exchange resin. And coming to the anion exchange resin that can be regenerated by washing with NaOH solution. That means whenever if we consider the exhausted cation exchange resin, when it is washed with sodium hydroxide solution, it readily reacts with OH minus ions and results in the formation of anion exchange resin. In that way, these cation and anion exchange resins can be regenerated. This is all about the removal of permanent hardness. Next, coming to the municipal water treatment. It mainly involves two major steps. One being the removal of suspended impurities. And the other one is removal of pathogenic microorganism. Removal of suspended impurities can be done by following 4 steps. First step is screening. Second one is sedimentation. Third step is coagulation. And the fourth one is filtration. Through screening method, the floating impurities can be removed from the water. And through sedimentation, clay can be removed from the water because of gravitational force. Coming to the coagulation, here the colloidal impurities can be removed by the addition of certain chemicals like alum or sodium aluminate, which is highly useful for the removal of colloidal impurities. Coming to the filtration, here sand filters will be used for the removal of all types of colloidal impurities and microorganisms to the certain extent. Next, coming to the removal of pathogenic microorganism, here we are having different options. Simply by boiling for about 10 to 15 minutes, the pathogenic microorganism can be removed from the water, or by the addition of bleaching powder. So, bleaching powder means calcium oxychloride, especially 1 kg of the bleaching powder can be added to 10 power 6 liters of water. Always calculated amount of the bleaching water should be added, otherwise it produces irritating odor to the water. So whenever bleaching powder is added to the water, then it results in the formation of slackline along with chlorine gas. This chlorine gas reacts with water and results in the formation of HCl and HOCl. It is called as hypochlorous acid. It is the actual disinfecting chemical. So whenever HOCl is added to the water, it selects germs and then germs are killed. Next method is by chlorination. This chlorination method is highly effective if the pH is maintained from 5 to 6.5. So chlorination method means whenever chlorine is added to the water, again it results in the formation of hypochlorous acid. Whenever hypochlorous acid is formed, It actively selects germs and thus germs are killed. But chlorination is effective when the pH is from 5 to 6.5. In that way, we are having the treatment with ozone. So whenever ozone is added, it dissociates into O2 plus nascent oxygen or atomic oxygen. This nascent or atomic oxygen selectively attacks on germs and thus germs are killed. If excess of chlorine is present, that also produces irritating odor to the water. Coming to the last technique, that is addition of chloramine. Chloramine is not readily available. It must be prepared by treating with chlorine with ammonia. Then it results in the formation of chloramine. So whenever chloramine is added to the water, then it results in the formation of ammonia and hypochlorous acid. This hypochlorous acid again reacts with germs and thus germs are killed. Here, if excess of chloramine is added, then it produces pleasant odor to the water, and hence this is the safe chemical for the disinfection of the water. Next, coming to the desalination of seawater. Here two methods are available. One is electrodialysis and the other one is reverse osmosis. And this reverse osmosis is best method for the desalination of seawater. Desalination means removal of common salt from the water. That is all about the brief idea of water technology. Now it's the time to discuss in detail about the multiple choice questions based upon the water treatment. Are you ready to answer multiple choice questions based upon the water technology? Which disinfectant does not produce irritating odor to the water? I am waiting for your answer. Option A, bleaching powder. Option B, chlorine. Option C, chloramine. Option D, none. What is your answer? Just give me your answer. S. Bleaching powder produces irritating water if excess is used. Chlorine also produces irritating water if excess of chlorine is used, and hence option C, chloramine, is the right option. Disinfection is the process used to remove option A, floating matter, B, pathogenic bacteria, C, minerals, D, colloidal particles. So especially disinfection is the process used to remove pathogenic bacteria, and hence option B is the right answer. Sterilization of water by chlorine is more effective when water has pH. So especially chlorine is more effective if the pH is maintained from 5 to 6.5. So coming to the given options, A below 6.5, B above 7.5, C below 9, D above 9.0. So option A below 6.5 is the right answer. The cation exchange resin possesses options. Option A acidic group, B basic group, C benzo group, D amino group. So cation exchange resin means RH. Definitely it contains acidic group. So option A acidic group is the right answer. The hardness of water is caused by option A undissolved salts of calcium and magnesium. Option B undissolved salts of copper and magnesium. Option C dissolved salts of calcium and magnesium. Option D undissolved calcium carbonate. Definitely hardness is mainly due to the presence of dissolved salts of calcium and magnesium. So option C is the right answer. Hard water can block radiators due to the formation of insoluble calcium and magnesium salts. Option B insoluble sodium salts. Option C insoluble phosphate salts. Option D insoluble potassium salts. In the radiators, very high temperatures will be maintained. Then all the calcium salts will be converted into insoluble calcium salts and magnesium salts will be converted into insoluble magnesium salts. So option A insoluble calcium and magnesium salts is the right answer. The exhausted zeolite bed excuse me. The exhausted zeolite bed can be regenerated by washing with. So exhausted zeolite bed can be regenerated by washing with what chemical? Option A NaCl solution. Option B dilute NaOH solution. Option C dilute HCl solution. Option D distilled water. So option A sodium chloride solution is the right answer. Hardness is expressed in terms of dash equivalents. Option A calcium carbonate, option B magnesium carbonate, option C sodium carbonate, and option D potassium carbonate. So hardness always expressed in terms of calcium carbonate equivalents. Which of the following is responsible for temporary hardness of water? A. Calcium carbonate, B. Calcium chloride, C. Calcium sulfate, D. Calcium bicarbonate. Especially calcium bicarbonate and magnesium bicarbonate are responsible for the temporary hardness. Yes, here option D calcium bicarbonate is the right answer. Which of the following chemical is responsible for permanent hardness of water? A. Calcium chloride, B. Magnesium chloride, C. Sodium chloride, D. Silver chloride. 4 chemicals are responsible for the permanent hardness. Mainly calcium chloride, magnesium sulfate, calcium sulfate. Here in this case, option B, magnesium chloride is the right answer. If you like the video, don't forget to like, share and subscribe. Thanks for participating. Have a nice day.